Hello students. Okay, so today we're going to talk about power series, which is 11.8 in your Stewart book. So here we have an example of a power series, and there are some functions like e to the x, sine x, natural log of x, that can actually be rewritten as a series, namely a power series, and that sum of that series would actually equal this function, equivalent to that function. So what does a power series look like? Okay, so here are some examples of power series. So you have a series and you have this expression an, which has its own function, and it is the pattern that the coefficients are going to follow. So an is the coefficients. And so here you have a coefficient, here's this coefficient, and so on and so forth. And then you have x to the n power. So that's where they get the power series from. Okay, so now the second one right here is your coefficients an, and then you have this factor, x minus c to the n power. And so you've got this. And you see here it's to the first power, here's to the 0, second, and so on until to the nth power, and it goes on infinity times. Now, when you have a factor x minus c, then it's a power series centered at c, and c is a constant. And there are lots of different ways of saying that your power series is centered at c. So I'm going to give you some examples. Here's this first one. Here, this one is centered at 0, because if you had x minus c, your c is 0 in this case, so that you can get just x to the 0 power, first power, second, third. And you can see that your an in this situation would be 1 over n factorial. So here you have 1 over 1 factorial, which would be 1 over 0 factorial, which would be 1. And then here it would be 1 over 1 factorial, which would also be 1. Here it would be 1 over 2 factorial, which is 1/2, and then it goes on. But this one is centered at 0. So you can say it's centered at 0. Here is another example. This one is centered at -1, or you can also say about -1. And so how you know it's centered at -1 or about -1 is if you rewrite this x minus c, then it would be minus a -1 for you to get this x plus 1 to the n power. And in this situation, your coefficient an is -1 to the n. And so it generates this series. And the third way of saying it's centered at something for this power series, you can say the following series is in, and then you state the factor, x minus 1. And when it's x minus 1, that means it's centered at x equal to 1, or you can say about x equal to 1. And so that's just stating what that factor is. And then in this situation, it's 1 over n are the coefficients for each of your terms. All right, so those are 3 different ways of saying what your power series is centered at. And then you can easily determine what your c is. In part A, c is 0. In B, c is -1. In part C, your c is 1. Okay, so now radius and interval of convergence. So best way to look at a power series is in this form, so that you can tell what it might be centered at, even if it was centered at 0. Alright, so the domain of your function is the interval at which the series will converge. Now, the first thing is that you need to always remember that your series can converge at its center c. And the reason is because when you substitute c in for x, it will turn all the expressions which you have to the nth power to 0. And so if you start off at 0, it will get, and you substitute 0 here, you'll get 1. And so then you'll just be left with your leading coefficient. If this was started off at 1, then your power series will converge to 0. In any case, just remember that wherever it's centered about, it will always converge at its center. So now you have 3 ways at which your function of your power series can converge. Okay, the first one is that it can converge at a single point, just at this point C, and nowhere else. Another is this interval that it can converge on, and this is a radius, capital R for radius of convergence. That's what that R stands for. And so the interval is going to be an interval that where your C is always going to be the center of. And then it can converge for the entire number line, meaning every value of x will allow your function of your power series to converge. So what it means for it to converge only at C, that means that your domain of your power series is a single point and the radius is 0. For it to have an interval of convergence, your x minus c factor must always be less than 0. And when you have this situation, you have an interval of convergence, which is centered at C, and your radius r is half the length of the interval. And then, of course, if the series converges absolutely for all x, then your domain is negative infinity to infinity, and your radius is infinity. So one power series that we had looked at earlier was a special infinite geometric series. So let's say that we have a power series where our coefficients an, all of them equal 1. And also that the power series was centered at x equal to 0. So if you have that, you will have this power series where f of x is equal to, so your an is 1 right there, and it's centered at 0, so you're left with just this expression x to the n. And when you expand that series, you get this sum. Now we want to determine what values of x will allow this series to converge. So remember that this one is, your first term is a equal to 1, and your common ratio r is x. So in order for this series to converge, you remember that your common ratio r has to be less than 1. So since our r is equal to x, absolute value of x has to be less than 1. And it will diverge for when your absolute value of x is greater than or equal to 1. And so then you have your interval of -1 to 1. And if you want to find the sum, the formula for the sum is 1 over 1 minus x, using the formula that we use for an infinite geometric series, a divided by 1 minus r. And so the radius of convergence is r equal to 1, which we get right over here. When we say absolute value of x less than 1, this 1 right here, that is our radius of convergence. When you have this absolute value expression and it's less than whatever is over here, that is your radius of convergence. Most often it's 1, and we'll find other problems where it's not going to be equal to 1. And then your interval convergence are the values of which x has to be in order for the series to converge. So we can see that our interval of convergence is going to be from -1 to 1. Finding the radius of convergence. Ignore the bottom part for right now. Okay, so you have this power series, and let's remember that n factorial is your an. Okay, so those are your coefficients for each of the terms. And then you have x to the n. So if we want to find out when this is going to converge, if you remember, we have a ratio test. And so if you put in your n plus 1 term and divide it by your nth term and take the limit as n goes to infinity of the absolute value of this ratio, you will get this expression. And then when we simplify that expression, so you'll have n factorial divided by, n plus 1 factorial divided by n factorial will leave you with n plus 1, and then x to the n plus 1 divided by x to the n will leave you with just 1x. Now we can factor out that 1x, and we will leave it in absolute values because we don't know what the x values are. So since it's a variable, we will keep it in the absolute value. But n plus 1, n is always going to be positive, and it's going off to infinity, so we can take the limit of this, and you could keep the absolute values on it if you wanted to, but you don't have to. And as n goes to infinity, you're going to get infinity. And so therefore, it diverges. But remember that all power series converge at x equals to c. So this power series is, that is centered at x equal to 0 converges at x equal to 0. And so even though it diverges for everything else, it converges at x equal to 0, which is its c. So this is what I just stated. It diverges for everything greater than 0 and converges at its center, 0. So the radius of convergence is r equal to 0. So now here's one that we're going to kind of work out together. We want to find the radius of convergence of this power series. Okay, now in this situation, let's remember that your an in this situation is going to be -3 to the nth power divided by the square root of n plus 1. Okay, and you can see that this one is centered at x equal to 0. And so by doing the ratio test, you take the n plus 1 term divided by the nth term, and you can see here I've already multiplied by the reciprocal. And so when you multiply by the reciprocal and you reduce, you will get this expression. There is one -3 left, there is an x to the first power left, and there's n plus 1 in the numerator, and square root of n plus 1 in the numerator and square root of n plus 2 in the denominator. And so now, since you're taking limit as n goes to infinity, you'll leave all of your n terms inside your limit, and you can factor out all your non-n terms and put it in front of your limit. And so you can have this expression. So absolute value of -3x multiplied by the limit as n goes to infinity of square root of n plus 1 divided by square root of n plus 2. And we know that this limit is going to go to 1. And so you're going to have absolute value of -3x multiplied by 1. And so for convergence, we know that by the ratio test, this must be less than 1. You can factor out your -3 and turn it positive. and then divide it out, and you can get that your radius of convergence is 1/3. Remember that once you get x by itself, whatever's on this side of the inequality, that is your radius of convergence. So now we're going to talk about endpoint convergence, which is different than radius of convergence. Endpoint convergence has to do with what happens at the ends of the intervals of convergence. So if you have a power series that has a radius of convergence r, then we need to look at the endpoints of that interval. You need to test each endpoint separately for convergence or divergence. So you can have lots of possibilities for your intervals of convergence. Here are various ones. If your radius is 0, we've talked about this, that it's just going to converge at the point C. If your radius is infinity, then it's going to be the entire number line. Negative infinity to infinity would be your interval of convergence. But now, if you have a radius of convergence that is a finite number r, but it's not equal to 0, then you're going to have this interval, where it's c plus r and c minus r for each one of these. But if you notice, these can vary. In this first example, the power series does not converge at the endpoints. Does not converge at the endpoints. It only converges within this interval convergence of c minus r to c plus r, but does not include the endpoints. For this one, you can see it includes the right endpoint. And for the third one, it includes the left endpoint, but not the right endpoint. And for the last one, it includes both endpoints. So you have these various situations where you need to test the endpoints to determine which of these situations you might have. So here's the first example. Here you have a power series centered at x equal to 0. And your coefficients, an, is going to be 1 divided by n. And so, again, we're going to do the ratio test. So you take the n plus 1 term divided by the nth term, absolute value of it, and then the limit as n goes to infinity. And when you write it all out and then multiply by the reciprocal of the denominator and simplify, you will get this expression, which again you can factor out. It doesn't show it here, but if you factor out your absolute value of x and leave behind n divided by n plus 1, you'll get absolute value of x to be less than 1, because the limit of n divided by n plus 1 is 1, multiplied by absolute value of x. And then you want in order for it to converge, this limit must be less than 1. So by the ratio test, the radius of convergence is r equal to 1. Okay, so since it's centered at 0, then this is your interval of convergence, -1 to 1. Although, remember we have to test the endpoints. So let's see what happens at each endpoint. So if you test x equal to 1 and you substitute it into your series for x, so when you substitute 1 in for x, you're going to get 1 to the nth power, which is always 1. So now this series can be rewritten as 1 over n, which is the harmonic series, which we know diverges. So therefore, at 1, this diverges. So we know that we're not going to include 1 in our interval of convergence. Now when we test x equal to -1 into the same series, it can be rewritten then as the sum -1 to the n power over n, which is an alternating harmonic series, which we've explored before, or you can just go ahead and do the alternating series test, and you will find out that it converges. And so therefore, when x is equal to -1, it converges. So what is the interval of convergence? It is -1, including -1, to 1, but not including 1. And so this is what it would look like on the number line. All right, so another example for interval convergence. Now this one we already did. So let's just review it. And we found out the radius of convergence is 1/3. And so since it's centered at 0, then this would be our possible interval of convergence from -1/3 to 1/3. So now what we need to do is we need to test each of the endpoints. So what we're going to do is we substitute in -1/3 in for x. And when you do that, you're going to have this expression, which then can be simplified when you put the -3 to the n power multiplied by -1/3 to the n power. You'll get +1 to the n all over the square root of quantity n plus 1. And so now, if you expand that, you can see that it is just a p-series, which I rewrote the sum to be at n equal to 1 to infinity of 1 over square root of n. I did that just so that it was easier to see what kind of p-series it was. You don't have to do that, but that's what I did so that it was easier to explain why this series would diverge, because your p is equal to 1/2, which is less than 1 when x is at -1/3. So it diverges at that point. Now you need to test the other endpoint, which is x equal to 1/3. And you substitute it in for x, and for x right there. And so then when you multiply 1/3 times -3, you're going to get a -1 to the n divided by square root quantity n plus 1. And that's your new series. And so now you want to look at this series and you decide, okay, is this going to converge or diverge? So you use the alternating series test. And when you do that, you see that your limit of your terms are going to 0, and that the next term is less than or equal to the previous term. And so therefore it converges by the alternating series test at x equal to 1/3. So it diverges on one endpoint and converges on another. So the interval convergence is -1/3, not including -1/3, to 1/3, and including 1/3. And that's the end. Good luck.